So we proceed now, move on to section 2.2. In this section we define what limits are. We discuss to the main concepts now are limits, situations where even though there are no limits in the usual sense, we can speak about infinite limits, and one-sided limits. Again, the problem is always what happens to a given function f of x as x approaches a number c, even if the function itself is not defined at the point c. So the book starts with an example. So let's introduce briefly a few examples that will motivate our discussion. And the starting point of the book is to consider the function f of x equals sine of x over x. So the question here is whether f of x is approaching anything as x approaches 0. And why is this question not trivial? Well, because f of 0 does not exist, so we can't just evaluate. So we can't compute sine of 0 over 0 and get 0 over 0. This is not a well-defined quantity. Okay, 0 over 0 is not 1, so warning. 0 over 0 is not equal to 1, ever. This is not a well-defined number, and as such we cannot just operate with it. I mean, expressions like this as if we were considering normal fractions. So this is the starting point. But maybe we can see that as x gets closer and closer to 0, this quotient here is approaching a given number. For instance, this may sound trivial, but this is another instance where there's a function that is not defined at the origin. Function g of x is equal to 3x over x. So g of x approaches 3 as x approaches 0. G of x, even though you can think that you can cancel out the x's, that's not allowed actually when x is equal to 0. So g is again not defined for x equal to 0. You cannot just plug in 3 times 0, which is 0, over 0 and cancel the x's. That's not allowed. However, if you look at the graph of g, the graph of g has a hole at 0, But at any other point, so this is g of x, at any other point, so this is the number 3, at any other point, the function is equal to 3. So of course, if we are approaching 0 from the right or from the left, g will be approaching 3. In fact, it's constant equal to 3. So it certainly has a limit. So this implies that the limit of g of x as x approaches 0 is 3. Because it is getting closer and closer to 3, and in fact it's equal to 3 for any value of x other than 0. And you may think, well, but this is a very easy situation because we can simplify for any value of x not equal to 0, and we get that the function is actually equal to a constant. Well, it's not so easy to do with, it's not so easy to do that when we're considering trigonometric functions like f of x here. So sine of x over x, there's no trivial way of canceling terms near the origin to get a limit. Okay, so somewhat of an intermediate example is the following one. So this will be the first way to compute limits that we learn, and this corresponds to just algebraically manipulating the expressions that we have at hand to obtain something that we can evaluate at the point where we're taking the limit. Okay, so what happens here now? What is the conflict here? What happens to g of x? So is g of x approaching anything at all as x is approaching 9? Again, we observe here that g of 9 does not exist. Again, because 0 over 0 is not defined. As you see, if you look at the numerator here, when you plug in 9, you get 9 minus 9, which is 0, and at the bottom we get the square root of 9, which is 3, minus 3, that's equal to 0. So we cannot compute the limit by simply plugging in the value of 3. However, we can do some algebraic manipulation. However, when x is not equal to 9, however, x can be taken arbitrarily close to 9. So you can get as close to 9 as you want. The only problem here for this expression, for the expression defining g of x, happens when x is equal to 9. But if you're close but not equal to 9, then you can perform whatever you want. And this is in fact what you do to compute this limit. So for x equals to 9, you can write x minus 9 over square root of x minus 3. as x minus 9. So there are two things that we can do here. We'll learn them both in time. First, we will multiply this expression by the conjugate in the numerator and the denominator. And on top, we'll just get, well, x minus 9 times the square root of x plus 3 divided by, and now we have the square root of x squared minus 9, and the square root of x squared is just x, so we get x minus 9, the square root of x times the square root of square root of x plus 3, all of that divided by x minus 9. Notice now that since x is not equal to 9, x minus 9 is not equal to 0. So this quantity is not equal to 0, and it's the same as this one. So we can actually cancel these two terms out. And we get an equivalent expression which is just the square root of x plus 3. So what happens now as x gets closer and closer to 9? So as x gets closer and closer to 9, square root of x plus 3 gets closer and closer to the square root of 9 plus 3. 3 doesn't change when you move x, but the square root of x is approaching the square root of 9, and this is equal to 3 plus 3, which is 6. Okay, so we can conclude then that g of x, the limit of g of x as x approaches 9, is equal to 6. And we accomplish this by performing some algebraic manipulations, simple algebraic manipulations. Okay, so this is the first way in which we're going to compute limits. We'll look at our expressions, and if they involve power functions, then they are completely algebraic terms and combinations of these. So no exponentials, no logarithms, or no trig functions. Then we can usually go about these problems in this way. Okay. So those are the examples that have to do with how to compute limits by looking what happens near the point. So, and this leads us to the actual definition of limit. So what are we? So far we've only discussed things at an informal level. So what do we mean by the limit of a function being L as x approaches a certain constant C? This is the definition of limit. And we write, I mean, we already written this in the previous section. So the limit of f of x as x approaches C is equal to L. We write this if f of x minus L can be made arbitrarily small, provided x is sufficiently close but not equal to c. Remember, this is the common problem that we had when we were trying to compute all of these limits. Starting with the first example, f of x equals sine x over x. Sine of x over x uh, both vanish at the, so the sine of x and x both vanish at the origin, so we cannot plug in the value 0 and obtain something that will tell us what this function is approaching. Neither does 3x over x or x minus 9 or square root of x minus 3 when we're approaching the point C, which in this case is 9. Okay, so this is the actual definition. So we want to make f of x as close as we want to L, provided that we can guarantee that x is close to, but not, this is the crucial thing, not equal to c. The value of f at the point is, if it has one, it's not relevant. The limit will not change. So let's try to see with an example. This is the only time we'll do this using the definition. The point here in the course is that we don't actually have to resort to the definition, but we learn some rules that will allow us to compute limits without actually having to perform this tedious computations every time. So let's consider the function 3x plus 1. H of x is 3x plus 1. And so we want to check that as x gets closer to and closer to 4, h of x approaches 13. In fact, you can look at this expression here, and if you were just doing some formula estimation, you would say, okay, let's look at what happens to this expression on the right. And 1, of course, is not changing, so it remains the same no matter what the value of x is. And the same is true for 3. But now x, as you get closer and closer to 4, well, x is getting closer and closer to 4. And so 3 times 4 is 12, plus 1 will be 13. So we have a candidate for a limit. So we suspect that this is the case. So let's try to see. This is true. So going back to the definition, we want to make sure that h of x is close to L, provided x is really close to 4. So what is h of x? 3 of x plus 1, and L is 13, and that's what we suspect. And here we get, inside the absolute value, 3x minus 12. We can take out a common factor of x. We get x minus 4. 3 times x minus 4. 3 is positive, so we can take it outside of the absolute value to get 3 times x minus 4. And you see h of x minus L is 3 times x minus 4. So if x minus 4 is small, h of x minus L will be small. Because h of x minus L in absolute value is just 3 times the distance between x and 4. Okay, so that proves that this is that the limit of h of x 6 approaches 4 is equal to 13. Okay, we'll be doing some other computations, and we'll go over the next items in our list in the next videos.